IIT Delhi developed the first version of autonomous car and showcased in IMC 2018. The 5G Indigenous testbed is today having a number of developed sub-projects and applications: the multi-access edge computing, energy harvesting, IoT, 5G security, and others.
Hello everyone, I'm Professor Brijesh Lal, and today I'm going to talk about MEC and see how it is a key enabler for tactile internet. This talk is part of the ANTS 2021 workshop on MEC and emerging applications, which is being held on the 15th of December 2021. In this particular talk, what I'm going to talk about is the tactile internet, what it implies, why is it important, why is there so much talk of tactile internet today, and then we will try to look at MEC and see why it is turning out to be an important element in the enablement of tactile internet. And then we will of course look at what capabilities of MEC enable the tactile internet. And this will be aligned to some of the requirements of the tactile internet. Finally, a couple of applications is what we're going to talk. So in IIT Delhi, we have set up an MEC and interfaced it with the core as part of the 5G inter-institute testbed that has been created with funding from the Department of Telecommunication. And as a part of that, what we've done is set this particular network up, and this is an example of what we have there. So we have a haptic setup, we have some camera based setups. In the haptic setup we have a robotic hand and a haptic glove. The two are connected to each other and they leverage the capabilities that the MEC provides. So on the user end side, through the G node B, you have the robotic hand, to which you send the command to perform manipulation of objects around it. And at the other end, towards the core or beyond the core, or at the MEC, depending on what architecture we use for a particular application, is the haptic glove, which is the one that gives the command and senses the feedback on how the robo is responding or what the environment, what's happening in the environment based on what the robo is attempting to do. And some of the things that MEC do here is they support intent prediction of degrees of freedom transformations, and if you do not do this, then the delay is so large that you cannot perform the tasks that you wish to accurately. So you could, for example, end up dropping something that you are trying to pick and move to another place. Similar things have also been enabled, for example, for video analysis. But in this talk, we will focus on the particular application, which is haptics based. So in the last slide, we will spend a little more time on the haptics application in the MEC environment. So you have the user equipment level. In the user equipment level, here you have the robotic hand as the device. So there's a client app running here, and there's obviously a device app, which contains all the drivers that you need to make this particular hand function. Here at the edge level, you have the MEC app service, you have the MEC platform, and at the remote level, you have the haptic glove. So you have the surface and infrastructure. So through the G node B, user plane function 1 connects to your MEC platform, where you have the apps which are connected through the MP interface to the MEC platform. The service is connected using the interface to the MEC platform, and the MEC host here runs a haptic support engine, which ensures that you are able to perform the task with ultra low latency with high availability and high amount of reliability. The security has not needed to be set up in this particular experimental setup, but that is also something that we will work towards inputting and enabling in this particular architecture. So all levels of capability, interfacing with the core and running the haptic support engine, the device app, the client app, making it all function, and also the corresponding apps for the haptic glove at the remote or the far end have all been implemented as a haptics demo. But that represents only one demo that we have set up. The core effort outcome was the MEC capability that we have built here at IIT Delhi and IIT Bhilai, and what we are able to now do is set up applications around this MEC setup. It has been interfaced with the core, and capabilities for it to interface with applications have been set up. So with this, I'll like to end this talk by stating again that tactile internet is here to stay. It is making small inroads, but soon there will be a deluge. There will be a lot more of tactile internet all around us. And when that happens, at least in the near term, in the way we view the network architecture today, MEC is a very, very important player in the ecosystem. Without the MEC, some of the key requirements of the tactile internet cannot be met. Thank you very much.
So we have the following setup for achieving the purpose. RAN emulator is where the client app and device app stays. So in this case, we have multiple client applications, one of which is object detection and a tracking application, and the other is face recognition. So in the first application that I'm going to demonstrate, a stream of video that contains two subjects is streamed from the client app to the system, and the MEC app has to process on the input, and whenever a region of interest is detected, it has to relay it to the server. So here I'm running the app. Prior to doing everything, a context has to be created. So a GET request followed by a POST request should be done. It has sent it. The device app has received this request, and now the UALCM will receive it and forward it to the MECO. MECO, upon receiving, selects the appropriate MEC edge, directs the MEC edge to for application onboarding and running the application. Now the MEC edge should have started running the application. Here it is. As we are able to see, the MECH has started processing the input as it receives from the client app. Now, as soon as a person of interest is detected, hereby we have set it as the trigger. The trigger mechanism ensures that whenever a certain condition is met, the input is relayed to a server, to a remote level server. And as soon as the person is detected here, it is relayed on the server. Here it is. The server is successfully able to receive the packets from the MECH. So upon successful completion of the lifecycle application, we are ready to terminate it. Another application that is deployed on the system is a tracking application, wherein on the client side, a camera feed is streamed and that contains pedestrians moving around, and the MEC app on the MEC platform has to process the input such that it has to count the number of bounding boxes it finds, and the trigger there that we have set is the number of people. When the trigger reaches a certain threshold, we are relaying it to the server. So here the application is currently rendering on the server when counter reaches 5 or greater than 5. All right. Now at the time of completion of the application's life cycle, its context is deleted and the app is terminated. This was it. Thank you very much.
Hello, we are going to demonstrate Wi-Fi communication network developed at IIT Delhi. This is the setup of Wi-Fi network consisting of one Wi-Fi transmitter along with two Wi-Fi receivers. The transmitter is transmitting two different video streams at 40 Mbps, which are received by these two Wi-Fi receivers. This functionality is achieved by implementing time division multiplexing, which enables multiple receiver communication over Wi-Fi. Now, let us demonstrate the functionality of Wi-Fi link. Here two different videos are transmitting. Now if we block the light path between transmitter and one of the receiver, then the data transfer stops for that receiver, and at the same time, the other receiver continues to receive the data from transmitter. This link also supports communication over wider area, which enables the movement of receivers in any direction. So if we move any receiver from point A to point B, the communication link stays intact. That's all for this demonstration. Thank you.
आईआईटी दिल्ली के छात्रों ने वायु प्रदूषण की निगरानी के लिए 5G तकनीक पर आधारित ऐसा डिवाइस तैयार किया है जो सौर ऊर्जा से चल सकता है। साथ ही जीपीएस प्रणाली से लैस होने की वजह से प्रभावी तरीके से जियो टैगिंग भी की जा सकती है। ये उपकरण शहरी क्षेत्रों में 10 किलोमीटर की रेंज तक PM2.5, PM10, NO2, ओजोन, कार्बन मोनोऑक्साइड और सल्फर डाइऑक्साइड की मात्रा का पता लगा सकता है। इसके अलावा इन छात्रों ने 5G तकनीक पर ही आधारित ऐसा स्मार्ट बिजली मीटर तैयार किया है जिसमें मीटर रीडिंग और बिलिंग के काम ऑटोमेटिक तरीके से होंगे। साथ ही इस मीटर के जरिए आप ये भी पता लगा सकते हैं कि आपके घर का कौन सा उपकरण कितनी बिजली खपत कर रहा है।
Usually the existing energy meter whatever we have in our households, they are not smart in a way that it is a bare meter only. Now the utility will send some person to collect the bill to your house. He will collect some readings and then will compute the bill offline, then you will get the bill, and these things are not automated. Now in this kind of smart meters, all this billing and all these applications are automated.
So we have used ZigBee APIs developed in Python to enable the transmission and reception of packets. Now we'll demonstrate the Diffie-Hellman key exchange protocol at UE1 and UE2. First, both the users will use a standard based or pre-agreed generator and prime number. In this example, they use G equal to 2 and the following prime number. They will randomly generate a private key at their ends, and using that, they will generate the public key by raising their private key to the power of G over modulo P. So now UE1 is sharing his public key with UE2. As we can see, UE2 has received the public key of UE1. Likewise, UE2 will share its public key with UE1. Both of them will now generate the secret key by raising their private key to the power of received public key of the other user. So they will end up having the same secret key as shown. For the illustration purpose, the secret key is in hexadecimal format and is 256-bit long. Using that key, UE1 will now encrypt the payload image using advanced encryption standard AES, and both UE2 and E will try to receive it. And as we can see, E will throw a decoding error as the image is encrypted and the data perceived is just the garbage, while UE2 using the secret key will successfully decrypt the image.